10.6 Calculus of polar curves. What you'll learn about slopes of polar curves, areas enclosed by polar curves. Slopes of polar curves are similar to parametric in that it's in terms of a third variable, which is theta. Let's go ahead and remember that y is equal to r sine of theta and x is equal to r cosine theta. Now remember, r is a function of theta. Now when I take its derivative in terms of theta, dy d theta, then I'm going to have to use the product rule. And so that's going to be f prime of theta sine of theta plus f of theta cosine of theta. Dx d theta will be equal to f prime of theta cosine theta minus f of theta sine of theta. Now that we have both parts, dy dx will be equal to the quotient of these two, f prime of theta sine of theta plus f of theta cosine theta, f prime of theta cosine theta minus f of theta sine of theta. All right, let's go ahead and apply this on the next problem. We want to find the slope, which is just what we were talking about. We want to find dy d theta, and that's going to be finding the derivative in terms of theta of r sine of theta all over d d theta of r cosine theta, which means I have to take the derivative of, and then r is a function of theta, so this is 2 sine of 3 theta times the sine of theta all over d d theta of 2 sine of 3 theta times the cosine theta. Now we can actually do this analytically, which I'll show in the next slide, or we can use our calculator. So I'm going to go ahead, second entry, and I'm going to show you how I set it up. So I use the derivative key, and in y equals, I have the 2 sine of theta, and you see I'm taking the derivative with respect to theta of r sub 1 sine of theta evaluated at pi thirds, and then I press the divide sign to do the denominator evaluated r sub 1 cosine of theta evaluated at pi 6. Okay, and then when I enter, I'm going to get this value. So this is approximately negative 1.732 ... or you might recognize it as negative root 3. All right, so I've answered the first part, but now the second part says to find the equation. And to find the equation, I need a point. So x is equal to r cosine theta, which means I'm going to take 2 sine of 3 evaluated at pi 6, and then I'll take the cosine of pi 6, and that's going to be equal to root 3 if you evaluate it. Y will be equal to r sine of theta, which is equal to 2 sine 3 times pi 6 times the sine of pi 6, and this will be equal to 1. So now I can write the equation of the line. This is the slope at evaluated at pi 6. So it'll be y take away 1 equals negative root 3 times x take away root 3. All right, the length of a polar curve. Now this is the parametric form, and this can be changed to polar form using this. So if we go ahead and find its derivative and evaluate it, it will simplify to this. And I'll give you a peek as to how that is done. So again, we're working with oops, we're working with this, and we are going to, instead of r, we're going to write f of theta cosine theta, and instead of this r, we're going to write f of theta sine of theta, and we're going to find its derivative. Here's the derivative, and we've got to square it. Here's the derivative of this, and we've got to square it. We're going to multiply it all out. Some things are going to cancel, and in the end, we're going to get these quantities right here, this and this. And when we square them and simplify, we're going to end up with this and an identity here that we can simplify to here, and then we can resubstitute f of theta to r, and f prime of theta is dr d theta. And so that's how it's done. All right, let's go ahead and find the length of the cardioid. Now, what I need is I need r, which is this, and I need dr d theta. So I'll go ahead and find that. That's negative sine of theta. So the length of my cardioid will be the integral, and I have to go through the whole cardioid. This will be root, and then I'm going to take my r, 1 plus cosine theta, square it, plus dr d theta, negative sine theta, square it, and then d theta. Put it in my calculator or evaluate it analytically, and we're going to get the answer of 8. All right, let's talk about areas enclosed by polar curves. Normally what we do is we just find the area between the curve and the x-axis. Now we're going to be looking at it as a sector. And a sector is, back in geometry, a sector is a portion of the area of the circle like this. Okay, one more time. Polar areas look like this. They look more like sectors, where ordinary integrals will have that rectangular look from the curve to the x-axis. All right, well, let's go back to geometry and try to find an area of a sector. Area of a sector. What we did is we defined it as m over 360 times pi r squared, so a portion of the circle. When we're working in calculus, we don't work with degrees, so this will be theta over 2 pi times pi r squared, and the pi's are going to cancel, and we're going to get 1/2 r squared theta. That's what we're getting right here. Now, these little sectors are going to be smaller and smaller to get more and more accuracy, and we're going to see a little small piece of area will be 1/2 r squared times times delta theta, a little small piece of a small change in theta. So the differential will look something like this. All right, so the area in polar coordinates looks like this. Let's go ahead and apply it. We need r, which is already here, and we need dr d theta. And that'll be equal to, well, this is going to be equal to 2 plus 2 cosine theta. So this will be negative 2 sine theta. So our length will be equal to the integral from 0 to 2 pi of 1/2 r squared, which is 1 plus cosine theta squared d theta. And now that I look at it, I really didn't need this. That's necessary for arc length, but not necessary for area, because the area only needs 1/2 r squared d theta. Now, if you want to do this analytically, it would look something like this, where you would expand it, and then at this point, you would have to use an identity to substitute it so that you wouldn't have any square terms in it. And then you would have terms that you could integrate each piece, and then you would get 6 pi. Okay, we're going to, here's the sketch of the rose curve, and we'd like to compute the area of one petal, which requires us to understand in the sine of 3 theta where it comes back to 0, where the curve comes back to the origin. And it starts at the origin and comes back at pi thirds. So this is the part that's difficult, setting up the limits of integration. So 0 to pi thirds, and it's going to be 1/2, and we're going to take the r, which is sine of 3 theta, quantity squared, and then d theta. And just put it in our calculator to figure out that area of that one rose curve.